We're not alone in detecting interstellar visitors anymore. What just happened with 3I/Atlas has every astronomer on Earth holding their breath, and the implications are staggering. Right now, hurtling through the cosmic void at a mind-bending 200,000 kilometers per hour, an optics from beyond our solar system is making its exit. We've aimed humanity's most powerful radio telescope directly at it, listened with instruments sensitive enough to detect a whisper from across the galaxy, and what we discovered in the silence is splitting the scientific world apart. The data just dropped, and I'm about to show you why this changes everything we thought we knew about interstellar objects. This isn't just another space rock drifting aimlessly. 3I/Atlas is only the third confirmed visitor from interstellar space in all of human history. Let that sink in. For thousands of years, we believed everything in our sky belonged to us, trapped in the sun's gravitational embrace. Then Oumuamua shattered that illusion in 2017, moving in ways that defied physics and ignited a firestorm of speculation. Borisov followed in 2019, proving interstellar comets exist. Now 3I/Atlas arrives, and suddenly 3 visitors in under a decade forces a terrifying question. Is interstellar traffic accelerating, or have we finally learned to see a cosmic highway that's been bustling with travelers all along? The numbers are almost incomprehensible. This object is moving fast enough to cross the distance between Earth and the Moon in less than 2 hours. At that velocity, our sun's gravity is nothing more than a brief suggestion. It's not staying, it's not orbiting, it's a cosmic hit and run on an unimaginable scale. That breakneck speed is precisely why scientists are in panic mode. The observation window wasn't years or even months. We had weeks, maybe days, before this thing vanished forever into the interstellar abyss. Before we dive into the radio scan that's causing absolute chaos in the astronomy community, you need to understand what's at stake. When we plot 3I/Atlas's trajectory, we see a steep, hyperbolic arc, the unmistakable signature of something that doesn't belong here. It dove into our inner solar system, whipped past the sun, and is now shooting back out into the void. But unlike Oumuamua, which tumbled and accelerated in ways that made physicist Avi Loeb suggest it might be alien technology, 3I/Atlas appeared normal at first. Optical and infrared measurements showed what looked like a standard comet, complete with a glowing coma and a tail of sublimating ice. Size estimates range wildly, from hundreds of meters to several kilometers, which drives scientists insane but reflects the brutal reality of trying to measure a supersonic bullet as it flies away from you in the dark. But here's where everything changes. While optical telescopes were counting photons, a different kind of instrument was preparing to listen. The scientific community realized that if this object was anything other than frozen rock and ice, anything artificial or technological, we had one shot to find out. If there was even a microscopic chance this was a probe, a derelict spacecraft, or something we don't have words for yet, we had to act immediately. We needed to listen, and we needed to do it at the moment of closest approach. The logic is elegant and terrifying. If you're a traveler passing through an alien star system and you're active, you might communicate, leak radiation, or use radar to scan your surroundings. Optical telescopes only see reflected sunlight, passive observation. Radial telescopes see activity, energy, intent. The decision was made. The Breakthrough Listen program, humanity's most ambitious search for extraterrestrial intelligence, secured time on one of Earth's most sensitive instruments. They weren't going to casually glance at this thing. They were going to interrogate it with unprecedented intensity. December 18th, 2025. That was the moment. The geometry was perfect, the distance minimized. If 3I/ATS had anything to say to us, if it was broadcasting, transmitting, pinging home, this was when we'd hear it. The anticipation in control rooms across the planet was electric. We weren't just looking for a comet anymore. We were looking for a technosignature, definitive proof that intelligence exists beyond Earth. A positive result would instantly rewrite human history, shatter religious doctrine, upend philosophy, and transform our understanding of life itself. But a negative result? That's where the real science lives. Because in radio astronomy, silence is never just silence. It's data. It defines boundaries. It tells us what's not out there, or at least what's not speaking. 3I ATS passed through our cosmic neighborhood under the gaze of our most advanced technology. We threw everything we had at it across the radio spectrum. What we found, or more accurately, what we didn't find, has triggered a fierce debate about our methods, our assumptions, and the very nature of how we search for life in the universe. The headline screams "no signal," but when you dig into the actual data, it whispers something far more complex about the limits of human perception. We're standing in the National Radio Quiet Zone of West Virginia, home to the Robert C. Byrd Green Bank Telescope. This is a monument to human ambition, a dish 100 meters across, larger than a football field, fully steerable, pointing wherever we command it to look. On December 18th, this colossal ear turned directly toward 3I ATS. This wasn't a casual observation. This was a targeted, high-intensity interrogation of an interstellar traveler. Breakthrough Listen has been scanning stars for intelligent life for over a decade, and they dedicated precious telescope time specifically because of this object's proximity and the narrow window we had to study it. The methodology matters deeply here. You can't just listen to the universe indiscriminately. You have to choose frequencies like tuning a radio to specific stations. The team scanned from 1 to 12 gigahertz, covering what astronomers call the water hole and beyond. This is a relatively quiet section of the radio spectrum, where galactic background noise is minimal and Earth atmosphere is transparent. It's the classic range where pioneers like Frank Drake hypothesized technological civilizations might transmit. This covers everything from our Wi-Fi and satellite communications to deep space radar frequencies. By scanning 1 to 12 gigahertz, they were effectively checking billions of channels simultaneously, hunting for anything that stood out from cosmic static. Here's the critical detail that changes everything. They weren't just looking for any broadcast. They were hunting for narrow-band signals. Nature is broadband. When stars explode, black holes devour matter, or quasars fire jets, they scream across the entire radio spectrum. It's messy, loud, everywhere at once. Technology is different. Technology is precise. When we transmit a signal, we compress energy into a very narrow frequency band to conserve power and carry information efficiently. A narrowband signal is the fingerprint of engineering, the hallmark of intelligence. On December 18th, the Green Bank Telescope tracked 3I/Atlas as it raced across the sky. The dish moved silently, compensating for Earth's rotation and the comet's rapid motion. Receivers were cooled to near absolute zero to eliminate electronic noise. Supercomputers crunched petabytes of raw voltage data in real time, performing Fourier transforms, breaking radio waves down into component frequencies. They were searching for a spike, a single sharp line on a graph that shouldn't exist, a tone, a beep, a sequence, anything manufactured. The sensitivity was staggering. The observations could have detected persistent signals down to power levels around 100 milliwatts. Pause on that number, 100 milliwatts. That's roughly the power of a standard smartphone connecting to a cell tower. Imagine a phone floating in the void of space, millions of kilometers away, transmitting back to Earth. The Green Bank Telescope could have seen it. That's the precision we're dealing with. We're not talking about needing a massive alien superweapon to be detected. We're talking about consumer electronics. If 3I/Atlas had a radio transmitter on board, broadcasting omnidirectionally in all directions, we should have seen it. If it was transmitting in the 1 to 12 gigahertz range with the power of a cell phone, the graph should have spiked. Alarms should have sounded. The team observed, recorded, processed, filtered out interference from our own satellites, which is a monumental challenge in radio astronomy. Distinguishing human signals from potential alien ones is harder than most people realize. They looked for Doppler drifts, the slight frequency shifts caused by the object's motion relative to the telescope, a telltale sign that a signal originates from the target and not from some terrestrial source. They did all of this with meticulous care. Then they published the preprint. The result was a flat line. No candidate technosignatures detected. No narrowband transmissions. No beacons. No telemetry. Nothing. In the scientific paper, this is presented as a strong negative result, and formally, it is. It establishes a hard upper limit on the object's radio brightness. We can now say with high confidence that on December 18th, 3i/Atlas was not emitting a continuous radio beacon in the LSC or X bands above 100 milliwatts. But this is where the science becomes fascinating and deeply unsettling. A negative result is not proof of non-existence. It's proof of non-detection under specific conditions. We've established our capability. We could hear a whisper. We've established the result. We heard silence. But what does that silence actually mean? Does it prove the object is natural? Or does it mean we were listening for the wrong thing at the wrong time in the wrong way? While the Green Bank telescope is a masterpiece of human engineering, it's not all-seeing, and 3i ATAS is proving to be a master of evasion. That 100 milliwatt figure sounds impressive, and it is, but it relies on critical assumptions. In the hunt for extraterrestrial intelligence, assumptions are the most dangerous weapons we possess. The silence from 3i ATAS is deafening. We pointed a 100-meter ear at the sky, capable of detecting cell phone energy across the void, and it heard nothing. The Breakthrough Listen team delivered their verdict: no techno-signatures. This contradicts what many hoped for, what imagination demanded. When an interstellar object enters our system, it's impossible not to think of Arthur C. Clarke's Rendezvous with Rama, of probes awakening as they approach a star, of a cosmic hello. But the data from December 18th is cold, hard, empty. A negative result in science is incredibly valuable. It clears the board, tells us where not to look, or at least what isn't happening under specific circumstances. We now know 3i ATAS is not a loud broadcasting beacon screaming its presence to the galaxy. If it were a derelict spacecraft with a functioning emergency transponder operating in standard communication frequencies, we likely would have detected it. The 100 milliwatt sensitivity rules out a specific class of loud artificial objects. It means if this is technology, it isn't behaving like our technology would. When we send probes like Voyager or New Horizons into the dark, they constantly phone home. High-gain antennas pointed at Earth, blasting data to the deep space network. 3i ATAS is doing none of that. But before we close the book and label it just another rock, we have to ask deeper, more uncomfortable questions. Is this silence absolute, or is it conditional? Think about this carefully. Do you believe a negative radio search is enough to prove an object is natural? Or could a technological object simply choose to be quiet? The paper states the sensitivity would have allowed detection. That's the critical phrase. It assumes a continuous signal. It assumes the signal was active during the observation window. But radio searches are snapshots in time by definition. Imagine trying to determine if a house is inhabited. You walk past the window for 5 minutes on a Tuesday afternoon. You see no one, hear nothing, detect no activity. Do you conclude the house is empty? Or do you conclude that at that specific moment, the occupants were quiet, in another room, or asleep? The Green Bank observation was a snapshot, an extraordinarily high-resolution snapshot, but a snapshot nonetheless. 3i ATAS was moving rapidly. The telescope was tracking. The observation lasted for a specific, finite duration. If the object transmits in bursts, say a millisecond ping every hour or every day, the probability of catching it during a brief scan is statistically minuscule. Furthermore, the search focused on narrow-band signals, the gold standard for SETI, because nature doesn't produce them. But who says an advanced civilization uses narrow-band radio for communication? Perhaps they use broadband spread-spectrum signals that look like noise to the uninitiated. Our own military uses spread-spectrum to avoid detection and jamming. If you examine a spread-spectrum signal with standard radio equipment, it looks like meaningless static. You need the decryption key. We don't have the key for 3i ATAS. Then there's the frequency range, 1 to 12 gigahertz. It's a massive slice of the electromagnetic spectrum, but it's not everything. We didn't search optical bands for laser communication, though other telescopes were watching, but not for nanosecond laser pulses. We didn't examine lower frequencies or higher millimeter waves. The strong negative result is actually a very specific, carefully bounded statement. We found no continuous narrowband radio signals between 1 and 12 gigahertz on December 18, 2025. That's not "there are no aliens," it's "there is no radio noise in this specific room at this specific time using these specific methods." This distinction is vital and often misunderstood. The public sphere constantly conflates evidence of absence with absence of evidence. We have an absence of evidence for radio transmissions, that's a fact. But inherent limitations in methodology prevent this "no" from being interpreted as universal. We're left with a puzzle. The object looks like a comet, acts like a comet, stays silent like a comet. Occam's razor, the principle that the simplest explanation is usually correct, screams that it's a comet. And yet, the very fact of its interstellar origin keeps the door slightly ajar. If it were artificial, why would it be silent? Is it broken? Is it a passive probe? Or is it simply ignoring us? These questions emerge when you stare at a null result long enough. The data is pristine, but interpretation is messy, subjective, fraught with uncertainty. There are scenarios, hypothetical but physically plausible, where an object could be artificial and yet remain completely invisible to the Green Bank telescope. We need to explore these shadows in the data, examine what we might have missed. Because in the game of interstellar hide and seek, the seeker has to be lucky every time. The hider only needs to be lucky once. If 3I-ATLS were artificial, how could it evade our best instruments? The first scenario is the directed beam hypothesis. Green Bank's search assumes an omnidirectional signal, a broadcast radiating in all directions. But if you're an advanced probe, why waste precious energy shouting into the void? You'd use a tightly focused beam, aiming your transmitter directly at your home star or a relay station. If Earth doesn't happen to lie in that narrow line of sight, and the odds are astronomically against us being there, we'd hear absolutely nothing. We could be staring directly at a functioning transmitter, but if the beam is pointed away, it's invisible. It's like trying to see a flashlight beam from the side without any dust or fog to scatter the light. You simply don't see it. The second scenario is deliberate radio silence. The idea that the object is intentionally maintaining silence while passing through a region under intense scrutiny. This sounds paranoid, conspiratorial even. It implies intent, awareness that we're here and listening. But consider our own submarines. They run silent when navigating hostile or unknown waters. If 3I-ATLS is a surveillance probe, its primary mission would be gathering data, not transmitting it immediately while under observation. It might store collected information and wait until it's safely back in deep space to burst transmit everything home. In this scenario, silence is exactly what we should expect to observe. The third scenario is exotic communication methods. We're listening for radio waves because we use radio waves. But radio might be the smoke signals of the galaxy, primitive, slow, inefficient. An advanced civilization might employ neutrino beams, gravitational wave modulation, or quantum entanglement for instantaneous communication across vast distances. These are channels modern astronomy simply doesn't monitor for messages. We're looking for messages in bottles while they might be using the galactic equivalent of fiber optic internet. These ideas lack direct evidence. I want to be crystal clear about that. There is zero proof for any of this speculation. But they highlight a crucial point. A null result in the radio domain describes the limits of our search methodology, not the totality of reality. The public is asking the right question. Does the absence of a signal definitively mean it's just a rock? The answer is probably yes, but not certainly. Then there's the space junk theory. What if it is artificial but dead? A piece of debris from a civilization that perished millions of years ago, a spent rocket stage tumbling through the void, a fragment of a Dyson sphere. It wouldn't transmit, it would just drift through the darkness, silent, cold, inert. In that case, radio searches would never find it. We'd have to rely entirely on physical characteristics, shape, rotation rate, composition, surface features. This brings us back to the hard data we actually possess. The radio search was necessary, important, but always a long shot. The real story of 3I-ATLS is written in its motion, its reflection of sunlight, its interaction with the solar wind. While we were listening for electronic beeps, NASA was measuring the physical reality of the object. Those measurements paint a picture that's less science fiction, more planetary science. But even there, the picture remains frustratingly incomplete. The object passed us at approximately 1.8 astronomical units, nearly twice the Earth-Sun distance. It didn't skim our atmosphere. It stayed out near the asteroid belt region. That distance makes optical resolution brutally difficult. We see a point of light, not a resolved disk. We infer size from brightness, which is why estimates range from hundreds of meters to kilometers. That's the difference between a skyscraper and a city, an enormous uncertainty range. Surface composition analysis suggests ice and dust because it developed a tail, the hallmark of a comet. But the precise chemical fingerprint of that tail is still being analyzed from spectroscopic data. We have a silent object, a fast object, something that resembles a comet but arrives from beyond the stars. The radio silence is one piece of a puzzle still being assembled in real time. As 3I ATLS speeds away, heading back into the interstellar night, we're left tracking both its physical trajectory and the scientific path we must follow to understand what it means. The excitement of discovering an alien signal has faded, replaced by rigorous, slow analysis of optical data. We're learning the galaxy isn't empty. It's full of debris, wanderers, travelers. Oumuamua taught us interstellar objects can be strange. Borisov showed us they can be familiar. 3I ATLS is teaching us they can be elusive, maddeningly ambiguous. Each visitor reveals something new about our place in the cosmos. They prove the solar system isn't a walled garden. We're part of a galactic ecosystem where material flows in and material flows out constantly. The investigation into 3I ATLS is winding down as it fades from view. But the search is just beginning. Breakthrough Listen continues its mission. The Vera Rubin Observatory is coming online soon, promising to discover not just 3 interstellar objects, but potentially hundreds in coming years. We're transitioning from the era of anecdotal discovery to the era of statistical population studies. Next time, we might catch one earlier, with sufficient warning to send a probe to intercept it. Missions like ESA's JUICE prove we can navigate complex gravitational environments, but we need revolutionary propulsion to reach interstellar objects in time. We might be able to touch one, drill into it, see for ourselves what lies beneath the ancient crust. Until then, 3I-Atlas remains a data point, a silent, speeding enigma. It's a reminder that the universe is vast, mostly quiet, full of mysteries waiting for the right moment and the right frequency to be revealed. But the story isn't finished. The silence itself is a finding, a constraint, a boundary condition. As we combine the radio null result with NASA tracking data, a final, conservative yet fascinating picture emerges. We've examined the speed, the scan, the silence, and the shadows. Now, as 3I-Atlas recedes into darkness, fading from even the James Webb Space Telescope's view, we must synthesize what we know and draw careful lines between what's possible and what's probable. The resulting picture shows that radio observations provide a clearly dated, quantitatively defined negative result. We know that on December 18, 2025, in the 1 to 12 GHz range, 3I-Atlas was silent, down to cell phone power levels. That's hard data, a constraint any future theory must satisfy. Simultaneously, this result underscores fundamental limitations of our instruments. We can only find what we're looking for when we're looking for it in the right way at the right time. The universe is vast, and our window of attention is vanishingly narrow. Against this backdrop, the conservative interpretation remains dominant. According to NASA, the object posed zero threat to Earth. It didn't approach closer than 1.8 astronomical units. It traveled through our solar system at 200,000 kilometers per hour relative to the Sun. These numbers tell the story of a natural event. A gravitational kick from a dying star or chaotic interaction in a forming planetary system eons ago ejected this chunk of ice and rock. It drifted for millions, perhaps billions of years, alone in absolute darkness. It fell into our gravity well, accelerated, heated up just enough to release a brief puff of gas, a cometary sigh, and is now leaving forever. It looks like an ordinary comet. It behaves like an ordinary comet. It emits no detectable radio signals. For the vast majority of scientists, this is the conclusion. Case closed. It's a messenger from another star system, yes, but a geological messenger, not biological or technological. It carries samples of the primordial material from another stellar nursery, not a greeting card. And yet, the very fact of this silence, observed within such a narrow and fleeting window, doesn't completely close the question. It establishes that at the specific time and frequency range we examined, the object was silent. It leaves that tiny sliver of what if that drives scientific curiosity forward. That sliver is where we live, where discovery happens, where the unknown becomes known. The universe is giving us clues, one object at a time, one flyby at a time. We just need to be smart enough, persistent enough, and creative enough to read them before they vanish forever into the infinite dark. Stay curious, stay skeptical, and keep your eyes fixed on the stars, because the next visitor could arrive at any moment.